Good morning, good afternoon, good evening, wherever you are, and welcome to the FAO Science and Innovation Forum, a webinar on circular food and agriculture system. My name is Rabi Mohtar. I'll be the moderator for this session and would like to give you an overview, the side event as part of the FAO Science and Innovation Forum. I'd like to acknowledge the organizations that are organizing this webinar, starting with the American Society of Agricultural and Biological Engineers, Texas A&M University, University of Florida, Michigan State University, and University of Illinois. Circularity in the food and agriculture system is a must as we move forward. If we know a little bit more about the Sustainable Development Goals and the targets that we have in front of us, and how much the food and agriculture system contributes to food security. However, it also contributes to several other unintended consequences, such as pollution of the air, pollution of water, and some risks to human and exposure to some of these pollutants. So the circularity of the food and agriculture system is intended to change the way we do business and intended to reduce our water, energy, food emission in the agriculture system, as well as it increases our resilience as we move forward. So the inputs to the system would be renewable water, renewable energy, recycled nutrient. And if we look at the anatomy of waste in the food waste, more than 40% of the food we eat is waste. That's not only food waste, that's a resource waste in terms of water, in terms of land, in terms of energy, and in terms of the other resources that goes into the food production. An outcome of the system is the nutrition, human-centric food system that we need to look at. So nutrition is a core to the circularity as we move forward. It's a reduced CO2 emission, reduced chemical reliance on chemical and biological pollutant, and reduced water, energy, food waste in the system. Last but not least, it reduces water, land, energy footprint. We're going to be exploring all of these in this session. Let me describe what we will be entering in the next 90 minutes to explore circular bioeconomy system, giving an overview of the systems thinking. So I'd like to underline systems thinking. And you're going to be hearing system all throughout the presentations. And there are protocols of field crop animal production system that we'll be exploring. The second item that we'll be exploring in this session is present examples of open and closed door discussion about the environmental, economic, and social sustainability of the food and agriculture system. Last but not least, we present the role of soil, tools, good practices, and limitation to transform this system. Soil is a cornerstone in what we discussed and what we will be discussing, because it's the interface we have with the environment. As I mentioned, I will be moderating this session. We'll start with a presentation by Dr. Ziynet, University of Florida, that discusses the food and agriculture system. The system approach to bioeconomy will focus on both open and closed production systems. Dr. Bruno Basso at Michigan State University will talk about circularity in the plant system, both open and closed. Dr. Angela, sorry about the Angela Green-Miller. This was a typo. I take responsibility for that. We'll be talking about the circular animal system and the interface with plant and animal in terms of the manure management. Dr. Green-Miller is at the University of Illinois. And last but not least, Dr. Samira Daroub at the University of Florida will talk about nutrient flows, nitrogen, phosphorus, carbon, and the economy of regenerative agriculture. And she'll give some practical aspects with examples on sugarcane production. And hopefully we'll have at 25 to 30 minutes of a discussion and a moderated discussion. As mentioned earlier, you could use the chat to ask the questions, and we will make sure that those questions will go to the right person in the panel. And the first speaker As I mentioned, is Dr. Ziynet Boss. She's assistant professor of sustainable food system engineering, University of Florida Department of Agriculture and Biological Engineering. She's done a lot of work in food packaging. She's done work also on sustainable food system, and she has been working on circularity and the digitalization of food system in Africa, and looking at packaging and processing. Dr. Bruno Basso is a John Hanna Distinguished Professor and MSU Foundation Professor of Earth and Environmental Sciences at Michigan State University. He's been working on agroecosystem and cropping system. He's a modeler and he's also a fellow at the American Association for the Advancement of Science, member of the Board of Agriculture and Natural Resources at the U.S. National Academy of Science and Engineering and Medicine, and a member of Biological and Environmental Research Advisory Council of the Office of Science at the Department of Energy. He's a fellow at AAAS and Soil Science Society of America and the American Society of Agronomy. He's a recipient of the 2021 Morgan Stanley Sustainability Solution Prize. Dr. Angela Green-Miller, at University of Illinois Urbana-Champaign, is Associate Professor in the Department of Agriculture and Biological Engineering, Department of Animal Sciences, and the Center for Digital Agriculture at University of Illinois Urbana-Champaign. She's the Director of Animal Welfare, Environment, and Sustainability Laboratory, co-lead of Livestock Research Trust, and she's the Chair of Diversity, Equity, and Inclusion in the College of Agriculture and Consumer Science and Environmental Sciences. She's the co-founder and president of Telltale Incorporated. Dr. Samira Daroub, University of Florida. She's a professor of soil chemistry, soil, water, and ecosystem at the department and director of the Everglade Research and Education Center. She's a fellow at the American Society of Agronomy and Soil Science Society of America as of 2021. She has developed best management practices to improve water quality as part of a comprehensive effort of the Everglade restoration. She's also been heavily engaged in education and extension project in the Middle East, India, in water resources, water quality, and food security. And as we go through the presentations, please use the chat to post questions and comments, and please keep your audio on mute during your presentation. Questions will be addressed towards the end of the event. I would like to give the floor, stop sharing, and ask Ziynet to do her presentation. Thank you.
Thank you, Dr. Mohtar. Let me share my screen. Okay. I hope everyone can see my screen. Okay. Hello, everyone. Today, I will give a brief overview about the circular bioeconomy in food and agricultural systems. I've been working actively with the ASAB Circular Bioeconomy Systems Initiative, and then I have also other projects on circular economy in my research program here at the University of Florida, but I'll try to give an overview to my best ability to cover everything here. So, when I was preparing my presentation, I was trying to find a representative figure that could represent agriculture and food systems, and it's impossible because it's such a diverse system and it involves several subsystems, and there is no one way to represent, of course, agriculture and food systems. So I tried to put some agriculture production data and then some post-production such as food safety and then food manufacturing. Of course, this is not an inclusive image, but agriculture and food systems, of course, starts from pre-production level all the way to the post-consumers, and then everything in mold in between. Because of that, it's such a complex system. So we have several problems in agriculture and food systems. First of all, we will be reaching actually exactly 8 billion in November 15. So that's the predicted number right now. So in a month, we will be 8 billion people. And then by 2050, we will be 9.7 billion. So feeding a growing population with changing diets, changing needs, it's such a challenge. And then it's a problem from food and agriculture systems perspective, because to produce these foods, we have to use a lot of water, a lot of resources, a lot of energy, and then labor. 80%, 70% of the water use, freshwater use, are due to food production activities. And then over 26% of greenhouse gas emissions are due to agricultural and food processing and manufacturing practices. While we produce enough food, we waste a lot too, and because of that, we need to produce a lot of food because we're nowhere near the eliminating the waste. So 30 to 40% of food, this is US-based data, but it's very similar in other parts, including developing countries, wasted. And then that wasted food is 8 to 10% of total greenhouse gas emissions. So that's a problem. So currently we are not there yet in terms of sustainability despite the efforts. And this is partly because of our linear systems that has been established since the beginning of the Industrial Revolution. The way we manufacture, the way we provide the foods is based on a linear system. So linear system is an economic model that involves very linearly taking and making, producing, and then disposing the materials, the resources, the use. So, and it generates a lot of waste. And that food and agriculture economy, of course, involves the production level, pre-production, production level, processing and packaging level. So two different industries coming together to process, and we consumed more than 70% processed foods minimally or over-processed, of course. And then distribution and retail system, supply chain, and then also household and consumer-facing outlets such as food service. So we are currently not there, and then we are our linear economies are our economies are based on linear approaches. So another alternative approach to this is basically taking a systems approach to economy and then minimizing the waste and then the need for new extraction of materials, raw materials actually, and then that's called circular economy. And then circular economy aims to regenerate natural food systems, design out waste pollution, and then keep products and materials in use by creating circularity options. And then in the ASAB CBS initiative, we actually added two more aspects to this from agriculture and food perspectives, which is provide economic benefits and increase use efficiencies. But there's also, on the contrary to common belief that circularity is reduce, reuse, recycle only, we have several options to create circularity options in our product value chain, product chains. So this is based on a framework, 9R framework, basically, and then all of them involve several aspects: refuse, rethink, reduce, reuse, repair, refurbish, remanufacture, repurpose, recycle, and recover. So this framework involves sharing economy, recycling, generating energy from the material. So there's not one way fits all approach in this. So we need to deliver those circularity options by creating small enough circularity operations or circles per se, and then keeping the circles operations very slow by slowing them down. Okay, sorry, it doesn't advance. Okay. But there's also another option where we can combine circular economy options, current circular economy options, with the bioeconomy. But before moving to the bioeconomy aspect, circular bioeconomy aspect, let me talk a little bit about the bioeconomy. So bioeconomy basically production of renewable biological resources from the agriculture, forestry, aquaculture sectors, and then conversion of these renewable resources and waste streams into value-added products such as food, feed, bioenergy, and other bio-based products. But the bioeconomy can also be linear too if we don't leverage that circularity aspect. And the combination of bioeconomy to circular economy actually created even a better approach and domain for us, which is called circular bioeconomy. And then it represents a lot people discuss, and then it represents the biological cycles of the butterfly diagram. And then the circular bioeconomy, in addition to circular economy and bioeconomy, combines these two concepts and then aims for the cascading use of biomass from biological resources using a systems approach for economic development. And then the idea is basically keeping the biomass properties high value and then high functioning as long as possible across the value chain, and then enable its use several times, so we actually reduce dependency to raw materials even more, the extraction of new raw materials even more. But also, of course, the biomass conservation based on the nature of the systems, nature on the application, and then the geography, and then the advancement of the circular bioeconomy, circularity of the system, it can go directly to bioenergy production, which is not desired in many cases, but still a circular bioeconomy. So there's several trade-offs, and then, of course, optimal outcomes, and that will be dependent on the application itself to determine which pathway to go. And as I mentioned, food systems is a very complex system, agriculture and food systems, and it's a systems of systems. So alternative approaches to create circular bioeconomy, of course, creating circles within each section or level of the system or overall systems. For example, biomass or ag production systems, we can utilize the biomass to manufacture I don't know, it can be bioenergy, right? Or biochar, for example, or we can go to the processing systems and utilize the waste to manufacture fertilizer, for example, from the processing waste, or some other new products. So there's several options, as I mentioned, but the overall value chain will require inputs of resources, and then it's also impacting the socio-economic environmental impacts, and then will create outputs and resource. And that's our approach to circular bioeconomy within the ASAB CBS initiative, to identify these different levels and then be able to represent that. So in this section, I'd like to talk a little bit more about some of the case studies and success stories from the US, from North America. I'm sure there are other applications already. And then there are several, of course, websites and platforms you can find those, but those are from the ASAB CBS initiative, Circular Bioeconomy Systems Initiative. The first one is USA Rice and Ducks Unlimited Rice Stewardship Partnership. This is from the production level, of course. And then in 2013, USA Rice and Ducks Unlimited formed the Rice Stewardship Partnership with a vision to conserve three interrelated critical natural resources: rice lands, water, and wetland. And then the platform has been used to conserve water over 42,000 acres of rice fields in different parts of the United States. And the second solution is the carbon dioxide capture and sequestration project. And then this is a partnership between ADM, Wolf Carbon Solutions, MGSC, and University of Illinois. And then they also achieved some great success by capturing the carbon and then 3-year monitoring of 1 million tons of carbon dioxide from ethanol fermentation at its corn processing plant in Illinois. And then currently 2 sites are in operation and have sequestered 3.4 million tons of carbon dioxide. And then my third case study example is from San Francisco. It's Planetarians. It's a company that uses brewer's spent yeast, which is the yeast remaining from the brewing process, and then distiller's spent yeast. So they bring these together with different dry byproducts with high protein content, and then fermented under controlled conditions, and then wet extruded, and then create meat, alternative meat proteins, basically alternative meat products. And then that saves a lot of water, 20 to 30 liter water savings compared to regular products, reduced greenhouse gas emissions, reduced land use and other benefits, and plant-based protein alternatives. So one of the ways to continue to demonstrate the benefits of circular bioeconomy is, of course, through case studies, and then measured metrics through case studies. And then with the initiative, we are hoping to continue to explore these applied nature and then the metrics that are measured. So that's all I think from me, and thank you very much for your attention.
Thank you, Ziynet. Bruno, next.
I'm mute. You can hear me and see the screen okay? Okay, great. Well, Rabi, thanks very much for organizing and moderating this very interesting session. It's truly a pleasure for me to be speaking to you today on how we intend are actually making pretty good steps towards circularity in grain production systems. So I just want to recap on the principle of circularity that was shown before, because the contribution by this ASAB initiative has really added components, and it really helps understand better the principle of circularity. The reason I'm showing it is because the material that I will be presenting, which deal a lot as the forum is intended to show the advancement in both science and innovation in the field of agronomy and the field of agricultural and biological engineering. So the increases in use efficiency is a component that you'll see pretty easily how beneficial it is and how we can tackle that. Consequently, you know, if you increase efficiency, you also minimize environmental impact and pollution, recycle products on the farm, and regenerate system, as more recently, most of you are familiar with the approach of regenerative agriculture. And ultimately, you know, we need to look after the economic benefits. There are very seldom cases where things are adopted unless there is also an economic benefit. Even from an environmental perspective, aspects, you know, need to go, you know, the monetarization of the ecosystem services such that farmers would benefit by implementing some of the practices that they are suggesting. One of the tools that we use that more recently, don't want to use necessarily a fancy word, but today we really are in a position to reproduce as a twin what happens in reality, but on a virtual system. So that starts by reproducing plans on the computer, not just visually, but with the details of reproducing the interaction of genomics, synthetic biology, crop simulation models, as you'll see here, able to capture the feedbacks between soil, plant management, be able to get output to the users on both profitability, environmental impact. And ultimately, that has moved all the way to the farm, where all this data, we have farmers that I work with that they physically have a virtual farm where all the soils and all the management, all the data is kept on the cloud, and it's used effectively to make more informed decision. The component that was presented, you know, the word that you'll be hearing the most during this is system, because without having a system approach, this circularity in the given the complexity of food system and agricultural system, so it's mandatory, and defining the system and the subsystem, it is the most critical step. This is a very simple example of a system boundary in the plant system in the center, where plants grow in the soil and produce grains, all the way to, you know, be able to have products that leaves the boundary, which basically drying and storage on the farm, but then going towards the sale. So separating and capturing carbon, nitrogen, and water dynamics into the system will allow to see how big the flows are, where the bottlenecks are, and what we're not really considering as a circular system. One also very important thing to realize is that agriculture, by definition, is a leaky system. So we work on soils and do not have an asphalt at the bottom. You basically have water going through, because we need to have that running into the aquifers at some point, but we also want to optimize the amount of water available to the plants. And so when we start use models like the digital twins that I presented, we can make decisions capturing spatial variability, which will be the next core of the few slides that I'll present, where this example here shows if you apply on a wheat field in the Mediterranean environment, where rain is pretty much limited from spring going onwards, there are areas within the field that if you add more fertilizer, these are rates 30, 60, 90. If you put more than 90 kilograms, you go towards 120, you would increase slightly the profit, but you start penalizing and start losing, leaching. In other areas, if you put more than 30, 0 to 30 and all here, you basically impact the environment and you lose money. And so the possibility of capturing this a priori and running for capturing even forecasted weather, be able to couple strategic decision with tactical in season, we will better tackle this environmental versus profit. And this is another good example from a study in Italy that we recently published with Lisa Schulte in Nature Sustainability. This is one of the most advanced systems where this company grows crops of diverse rotation, the apotheosis of regenerative agriculture, and then uses manure from livestock from all the areas close by in the Parmigiano cheese consortium. They get feed into the biodigester, generates biogas that gets sold on the grid, and the biodigestate, the digestates gets applied back into the field. Now I'm working closely with them to basically spatially variable input and put only the amount where it's needed and be able to distribute in areas where they can take it more. And so that's an example of a very closed loop circularity by going across system, both plant and animal. Now, moving quickly into digital agriculture, what has really happened? This is both the US and most of high-income countries have been highly affected by the possibility of investing in machinery that have sensors. And so you can collect now information and know about your yield mapping and variability within the field. The problem is that plant use and see whatever they are exposed to, whether it's climate, position in the landscape, inappropriate management. So variability is not just soil centric. If it was just soil centric, the maps will look alike every year. And unfortunately, they don't. So one of the algorithm that I've developed and scaled across large areas is by integrating, instead of using yield mapping where they were used to validate, we integrated layers from remotely sensed image at different resolutions and scale and developed this yield stability. So integrating years of imagery into one single layer where it captures the spatial and temporal variability, but also how stable they are and how unstable, how they flip-flop from one year to the next. This basically is the most important layer to increase efficiency, because you would be able to understand that a low and stable areas that is being managed even with sufficient amount of input, it still gives you low yield. That's a very good indication where you should be reducing your nitrogen application. So now we have a possibility. This is, I guess, still impresses me. This is daily images every single day, 3 meters on the ground, that captures the variability of a very large farm. And be able to do this now, we, again, like what I mentioned, we can pretty much see just about anything happening on Earth and the changes from one place to the next and over time. And so one of the most recent work, by understanding for the first time scales for precision agriculture and understanding you can click on any single paddock, any single field, and be able to characterize the yield stability, which takes it to the next level of a life cycle analysis and quantifying the impacts. And so 48% of within field variability had a nitrogen use efficiency of 75%. But the low and stable areas, which are a large amount, there are 25 million acres here in this particular example, 45% is the best nitrogen use efficiency. So basically 55% of the fertilizer used was just basically going into the water, with the impact that you see there on the, both fertilizer, the economics, and the energy loss and CO2 into the atmosphere. We're also trying to understand, and we have a knowledge now where the vulnerability of the system, where water tends to be, areas within the field tend to be affected more by water deficit versus excess water. One of the few places in the world we can grow corn on 90 million acres, mainly rain-fed. just because we have sometimes opposite problem. Too much water that stands in the field doesn't help the farmers getting into the fields in time, which is another major cause of yield variability. So again, the webinar calls, innovation in agriculture is moving extremely fast. There are public-private partnership moving this technology together. One of the addition is by understanding what I've just mentioned is the spatial and temporal variability. Those are for time, I won't be able to show basically how much money a farmer will lose on these areas, but from a profitability map, you can make this double decision, whether you say, is it better to go for ecosystem services and increase biodiversity? So we have a project that basically pays farmers as a form of incentives to remove the low stability, as you'll see in this map on the lower right, and plant the native vegetation pollinators, and they get an incentives from NRCS of the cash rent. So they don't lose even though the yields are lower, but they would still sell those yields. Now they get paid from incentives as well, potentially on a long term, they can sell for carbon credits. So this year at the lab distributed 25,000 hectares of yield maps across the US Midwest to farmers. And just this is an example that I quickly extracted from Michigan, showing the validity of the approach in the sense that high and stable zones had the same yield, whether you use uniform versus variable rate. And if you move into the efficiency increased with the variable rate, but the yield was never penalized compared to the variable rate. So in the end, my last slide, I encourage people, given time, I'm not able to really go in all the details, but these papers that we recently published in Egg System and the Proceeding of National Academy of Sciences show how this is the current system that we deal with. But we showed with a very detailed life cycle analysis that agriculture could be 70% negative. And the technology is divided in what is currently available, 0 to 3 years, 3 to 15, 15 to 30 years. And by basically, again, capturing carbon, including renewable energy, moving animals into more grassland, building carbon, capturing water, improving, overwash electrification of the fertilizers. And so it is pretty complex, but invite you to read the papers to get the full pictures. So again, I want to thank you for the invitation, and I thank both the investors, the agencies, and the members of my lab to make this work significant. Thank you very much.
Thank you, Bruno. We're going to switch to the animal system. Angela.
All right, thank you. Let me get my screen shared here. All right, can you see my screen and hear me? Good. All right, fantastic. So again, my name is Angela Green-Miller at the University of Illinois, and I work in animal systems. So that's where we're going to spend a little focus for a few minutes here. I appreciate the opportunity to share today and engage in this conversation. And I'm excited to hear all of these different pieces converge in a common conversation. So that's fantastic. So we're going to start in this section today by looking at some visual representations of circularity. Within this presentation, I opted for very little text, so mostly show and talk is what I'm going to call it. So this figure is a model bioenergy system that was redesigned during a breakout room in a workshop that was held this past summer, the Circular Bioeconomy Systems Workshop at the ASAB Annual International Meeting. So for those unfamiliar, ASABE is the American Society of Agricultural and Biological Engineers, one of the hosts of this session today. And so this figure is a little preview of a summary article that's going to cover that workshop, and it will be coming out in a future installment of the Resource Magazine, which is produced by ASAB. The article is also going to highlight some upcoming events that include CBS Day that's going to be held next year at the ASAB annual meeting in Omaha, Nebraska in the US. So just a little plug here, you're all invited. And if you want to keep an eye on the details, the website is there at the bottom right corner. Let's take a look at this figure to start with. On the figure, you can see representations of three fairly typical agricultural production systems, and you can see some connection points. So the 3 circles show corn, pigs, and the abattoir for processing the meat. And these are typically operated separately, and the connections that you see there in black show the products that really move between them. So grains going to feed the pigs, and then the pigs to the processor, and then meat out to the consumer. Now, if we zoom in a little bit to focus more on the animal systems pieces, we can kind of see the blue arrows are representing original inputs to the system, and the red arrows are representing outputs, output flows. And then the green text in the arrows are representing new modifications to the system's mass and energy flows. And they would enhance the circularity of the system. So you can see there are a couple of new connections that are proposed between the subsystems, such as a digester to take waste from both the animals and the processing. So thus creating some new linkages across those systems. Now, this figure is missing a lot of the components, so I'm just really using it to get us thinking in that direction. In our current systems, we already have many practices that add circularity to the systems. So we can increase circularity by improving upon those existing linkages, or we can do it by creating new linkages. One of the critical considerations for creating new linkages involves working across some of our historical disciplinary boundaries. There are lots of advances to be made in improving circularity with our existing flows for animal systems, both in sourcing inputs and in redirecting waste outputs. We can look at the system by specific nutrient flows, energy flows, and we've seen a couple of those in some of the talks already, and in the one that follows me as well. If we want to really think about new linkages across typical disciplinary silos, then we have some opportunities to get way outside the box. So for example, we could think about co-locating systems that have not typically been in proximity in order to better link flows without the addition of new transport, or to remove the losses of transport in existing systems. So what we'll do for the rest of our time is step through an example system to highlight some of the existing linkages and opportunities to improve their specific to animal systems, and then also creation of some new linkages. So this case that I'm going to share is inspired by one of those breakout sessions that was in the CBS workshop this last summer at ASABE. The schematic is hypothetical. Some of the processes that I'm going to highlight, they exist and they're in practice, and some of the others are experimental or theoretical at this point. For the sake of keeping this talk short, so within 10 minutes, I've omitted a lot of the specificity with numbers and animal species, with the intent that I want to present a framework for consideration and to spark conversation. So here we go. If we want to dig into animal production systems, we should think about the purpose of our animal production systems. The primary goal in animal production is to produce high quality protein. So this is the desired endpoint, and everything else is a process to get to that point. So let's step backwards and look at a system that gets us there. We start with our production barn, or if we're in open field, our grazing field, and we pick a species. Now, I do think that we'll continue to need large-scale animal production in order to meet the global requirements for animal products. So this example isn't looking to integrate a multi-animal system and scale it. So I would say, I've got a bunch of different animals up there, but if we want to move this into practice, we need to pick one. And what you choose really should depend on access to other resources, geography, and supply chain infrastructure. So that's our first place where we can think about improving circularity, is locating our systems in places that really make sense with the flow of nutrients, the flow of energy, and the availability and of both the inputs and the opportunity to use the outputs. We do need a number of inputs into the system. So this includes feed, water, energy, labor, and we can continue that list. For consistency with that prior figure, I've kept the blue arrows as the convention to represent our inputs. Beyond the farm, we can expect to need some processing and distribution to get from our animal production to our consumer-ready product. And we will have wastes coming out of the system, which may be nutrient heavy, such as manure. We might have thermal energy from the animals, metabolic byproduct gases going into the atmosphere, and other wastes that are specific to farm activities. For example, plastic waste from artificial insemination on breeding farms. Processing will also contribute to the waste stream as well, both in terms of biological wastes as well as energy wastes. And if we start to think about what we do with those wastes, manure coming off the farm, as an example, has long been used as fertilizer and taken back for land application. This is, a historical circularity success, and there's a lot of science and engineering that's helped to plan, to prepare, and to scale the redistribution of nutrients as the size and locations of farms has scaled. The current state of the art is not without challenges, though. Especially in areas where the availability of the manure waste, so the places where we're growing the animals, outsizes the land demand or the opportunity to utilize those nutrients. Or when we see things like severe weather that creates failure points in the system. Now, within what exists, there are a lot of opportunities to do better. So you can see I've added some green arrows in our inputs to the system to show this. So some specific examples, we can source feed from better production methods that are more circular. So coming out of that cropping system that has better production methods. Potentially sourcing feed inputs that are wastes from another stream. So an example of this in practice, feeding distillers dry grains or DDGs is an example of practice using a waste product from fermentation of corn for ethanol fuel. Other examples include more efficient water usage or water recapture, treatment and reuse, more efficient facilities, like thinking about energy efficiency of fans and lighting. In a grazing-based system, most of these distributions back to the land are just built into the system, but the way the animals are managed on that land can have significant impact on the soils and the water. So in these last couple of minutes that I have, let's move toward thinking outside the box. So if we revisit our end goal that we highlighted at the very beginning and ask ourselves, are there ways that we can yield even more high quality protein by capturing the energy that is lost from the waste? We already see this a lot in aquaculture. So where wastewater from one fish production is recycled down to the next type of fish as an input, and then down to the next type of fish. And so basically taking the waste from one as an input to the other to capture those nutrients and the energy that is being lost as waste from one. So can we do this with some of the waste from our land-based animals? And if so, what might we be able to produce? So we could probably grow some alternative plants, so things alternative to our open field grains or fruits and vegetables. An example that might be mushrooms. So we could maybe create an indoor mushroom facility to utilize some of those wastes coming out. But let's get even a little more outside the box and think what might help us get closer or more towards high quality protein, if that's the end goal of our system. We already share some things across animal systems, such as bone meal from cattle that goes into the laying hen feed. And that's good. And there are likely more opportunities to redirect different inputs in that way. But let's just for a minute, look at something we've never seen before. So what if we paired two existing systems on the same site instead of trucking inputs and outputs? So you can see I've added a barn here with the green arrow. So in this adaptation, we could consider producing bug-based proteins such as grasshoppers or worms or beetles, utilizing discarded energy supplies from the original animal system. So this may be nutrient waste from digestion or thermal waste from metabolism. And if we want to further get outside the box, we could even think about the plants that are needed to feed the bugs, and can we capture some of the waste to also grow additional plants to feed the bugs. We should still expect that this sister system will need some other inputs, and many of them will be similar and might be shared with the inputs as the original system. The sister system will also have some waste, and the goal is that it's recaptured some of the losses so that there are fewer wastes per unit of protein produced. We can expect that we'll still need processing, and there will still be some processing waste, and that the processing needed is likely very different from what we need for the processing of meat, milk, and eggs. Which brings us to that end goal. We can see products emerging now in this space, such as protein drinks, energy bars that are bug-based protein, or gummy supplements that offer another path to high-quality protein. So I'm going to end here with a couple of questions to consider about any of the circularity improvements that have been suggested within animal systems. So hopefully these questions will kind of spark your curiosity as we move and get closer to our open discussion. So here's some considerations. Does the financial incentive of this new process or product generate sufficient added value or savings to make sense for the producers? Is there an improvement in circularity, or are we truly better utilizing our resources, or are we just shuffling around the inputs and wastes and giving them a new label? Are there other factors that might make the system more challenging to implement, such as logistics or pairing production cycles to the needs for inputs and use of the waste? And for example, in our new bug-based system, are there biosecurity constraints? Are there ecological concerns for bug containment? And if we're considering the sentient beings in our system, are our changes creating any undesirable outcomes for the welfare of the animals or the safety and health of the workers? So with that, that's where I'm going to wrap up and encourage questions, discussion, and any of that after all the speakers have presented. So thank you for your attention.
Thank you, Angela. Last
unshare
would be focusing on the nutrient flows. Samira?
Okay, thank you, Rabia. And I will be talking about nutrient flows, as Rabia mentioned, but a little bit more finer scale than the previous speakers. I chose to focus on carbon, nitrogen, and phosphorus because really these three elements affect the soil's ability to provide the conditions needed for a sustainable crop production. So this has been mentioned a little bit before by Bruno and others. What are the losses in the carbon, nitrogen, and phosphorus cycles? What is done and can be done at the farm level, and then give you an example about the industry role and economics, an example here from South Florida working on sugarcane. As you all know, soil organic matter is, of course, a lot of carbon, 58% carbon, but it is the biggest source of nitrogen in the soil. Actually, about 98% of nitrogen is organic in nature. So managing organic matter not only impact carbon, but nitrogen as well. And as has been mentioned before, the mineral nitrogen, the inorganic nitrogen that we deal with for plant uptake is a very transient nutrient in the soil. It does not stay. There is a lot of losses in the nitrogen cycle, including nitrate leaching, denitrification, loss of nitrogen as gas, as also ammonia volatilization as ammonia gas from the soil. So managing carbon and nitrogen is essential, and there are key challenges for that. So we want our soils to be a carbon sink. There's always decomposition of biomass in the soil. There's always decomposition of residues, but we want to manage our soils to be a carbon sink and sequester more carbon than it releases into the atmosphere. So how do we increase soil organic matter in the soil? Definitely, there's a lot of initiatives to improve soil health, and climate smart agriculture is a buzzword these days. There's a lot of things that can be done at the farm level, including cover crops, use of legumes, but other cover crops also to reduce soil erosion. We've talked about manure, addition of manure, compost, biochar, these are all available. With manure, I have to add the environmental impact is really real in terms of the impact on water quality, but also on food safety. And sometimes the economics do not make any sense to add this manure or haul it long ways. We can also focus on tillage, minimum or no tillage. regenerative agriculture advocates for the use of farm animals. There's a lot of debate nowadays. It's really a buzzword to use regenerative agriculture. How applicable is it to large systems that we have here in the United States and Western Europe, as well as the economics of it? So I would say every system is different, and we have to look at the local issues to see if the economics make sense and if it's applicable to these systems. And of course, forestation, to be able to sequester carbon, is another value, and that can be added. So I want to talk a little bit, just a few slides about increasing soil carbon. Not one management practice can lead to that improvement in soil carbon. Things can be very local in terms of what are the cover crops that is used. This is an example from Alabama to increase soil carbon. They found that mulching and high biomass mulching works much better than cover crops, for example. This is an example from us here in South Florida. We did a bit of modeling how to increase peat in South Florida soils. We have a lot of organic soils that have been decomposing and releasing carbon dioxide to the atmosphere because of drainage and oxidation. And what we found out that it's not just one practice that increases soil organic carbon, it is a combination of practices, including high water table to reduce oxidation, incorporation of residues. So biomass residues, whether it's mulching or in this case, is sugarcane biomass, made a big difference, as well as improved cover in the soil. So the other key challenges for nitrogen, of course, is to reduce those nitrogen losses from the cycle, whether it is nitrate leaching, but also the gases. There's a lot of practices for fertilizer, manure, and water management, as well as cover crops to take up the leftover nitrate. If we want to have a circular system in terms of what farmers can do, we have to rely on soil organic matter and mineralization of soil organic matter to give us some of these nutrients, including nitrogen and phosphorus. So how can we guarantee farmers to rely less on inorganic nitrogen? Is to basically to figure out how can we estimate that amount of nitrogen being mineralized and the time, and synchronize it with when the crop needs it. There's a lot of factors that affect mineralization. Soil water is a big one. So there's an optimum water content for this mineralization, but then when you have more water, these are three soils of different texture. A sandy soil can leach quite a bit more nitrate compared to a clay soil. So a clay soil can have residual nitrogen that we can use cover crops to take over, but a sandy soil will basically have no nitrogen at the end of the season. I want to move on and talk a little bit about phosphorus. So phosphorus is different from nitrogen. Nitrogen doesn't have a residual impact in the soil from fertilizers, but of course, there's a lot in the organic matter. Phosphorus, we put a lot of phosphorus in the soil for either fertilizer or manure, but the availability is really impacted by the soil chemistry. So talking about tropical soils, there is a lot of reduced availability because of these fixation reactions that can happen in both calcareous and tropical soils. But also in some environments and some soils where we've added a lot of nutrients and added a lot of manure, you have quite a bit of loss, either in runoff, but also soil erosion. And the last issue of phosphorus, I would say, for the circular economy is the finite source of fertilizers and finite source of phosphate rock to produce phosphorus fertilizers. So what researchers that work on phosphorus, and there is a lot of us, really focus on how can we mine the phosphorus from the soil. This is a map from Pedro Sanchez showing the phosphorus deficits as well as the phosphorus surpluses. So definitely some areas of the world, there are phosphorus deficits, especially in probably tropical Africa and maybe in South America a little bit. But on the average, there's a lot of phosphorus surpluses, again, from addition of fertilizers. These statistics in terms of fertilizer efficiency of phosphorus is staggering. Only 10 to 20% of phosphorus fertilizer applied is recovered, and up to 36% is recovered in the first two crops. So there's definitely a lot of residual phosphorus in the soil that needs to be mined, and how can we make that phosphorus more available, especially in acidic tropical soils. So legacy phosphorus is estimated, again, this is from Satari and Sanchez. This is how much is accumulated over the last 40 years in terms of legacy phosphorus, even in Africa, because of the less efficiency of phosphorus uptake over there, but definitely in Western Europe and North America. So I feel one of the research impacts, or one of the research focus that needs to be done, is how to improve that utilization efficiency of the residual phosphorus. I'm showing you on this slide some of the impacts of crop and maybe different cultivars that can be used that are more efficient in phosphorus acquisition. This is a capacity of a legume, which is a faba bean here, to take up phosphorus from very low availability sources by reducing the pH of the soil. So it reduces the pH around the rhizosphere to 3, 4, and 4.5, and it mineralizes or releases some of the phosphorus that is residual, and it mines the phosphorus. But definitely for phosphorus, we need better calibrated soil tests for crops, mobilize that residual phosphorus. I think this is a high need for research, management of manure that you guys have been talking about, and perhaps capture more from sewage treatment plants. In the United States and Western Europe, the issue is excessive phosphorus in the soil and how to have more of that phosphorus kept in the soil and be used eventually by more crops. Just a few slides, a few graphs to show you some soils from Delaware, but also the Netherlands, how addition of manure over a long time has increased phosphorus concentration. This is available, this is not total phosphorus in the soil, to a really high degree that definitely impacts between runoff, erosion, and even leaching, in that sense, if it's a sandy soil, to pollute surface runoff and the impact on eutrophication and water quality. So the last few slides, I want to just show you an example from South Florida regarding Everglades restoration and the use of mandatory pest management practices to reduce phosphorus transport and keep more of phosphorus in the soil. This is a mandatory program in the Everglades agricultural area that has been implemented since 1995, where farmers do a lot of pest management practices. The average reduction has been, since the last 25 years, almost every year about 50%. The average reduction is 55% load reduction. But we don't just stop at BMPs. The state of Florida, as well as the federal government, has a lot of regional construction projects. These are constructed wetlands to be able to clean up the water and take more phosphorus from the water before it moves into the Everglades. The ultimate goal is to have water as low as 10 parts per billion. The practices are many, related to nutrient management, soil testing, band application, sediment controls, reducing soil erosion, as well as water management. And finally, my last slide is the impact and the involvement of industry. Any practice that we introduce has to be economic in nature, to be adapted by the industry. So I talked about BMPs, and this is from the sugarcane industry in South Florida. This is the same industry that show there is a lot of waste products that being generated. It's called bagasse. What they did is they got together and formed a company called Tillage. This new company took the bagasse fiber, and they're now producing sustainable tableware, food service products that decompose fast. It composts in about 84 days. But not only that, a lot of this biogas is also generates biogas, and the industry, the plant is powered by this renewable biomass from the sugarcane fiber, and the manufacturing facility is just adjacent to the sugarcane mill. So a waste product that is taken, used for power, used for making tableware, that composts and goes back to the soil. And thank you very much for listening to me.
Thank you, Samira. Thank you, Ziynet, Bruno, Angela, and Samira, for a very well articulated message about the circularity of the system. I think it's about time that we really transform that. Before we kick off the question, there are a couple of interesting questions in the chat. I'd like to pose 2 questions for the panel, and you don't have to answer all of them, just if you have some thoughts. And I really would like to invite, if anyone in the audience is a producer himself or herself, I would ask that you step forward, because some of these are challenges that will be faced by the producers. So the first of the question I'd like to pose, many farmers, many producers would actually tell you, yeah, I would like to, this all sounds great. But there are a lot of bottlenecks. So if you could maybe highlight what are these bottlenecks for transforming the system. The second question are, there are technologies, policies, and behavioral changes to transform the food and agriculture system. What are, in your mind, top technologies, technologies, behavioral changes, and policies that need to change?
Do you want us to start?
Yes, please.
Yeah, well, I'll kick us off, and I'll start by highlighting some of the things that the ASAB task force on circularity has been kind of talking about, is the existing infrastructures that we have, especially on the science side, often are very siloed by discipline, and the working across those silos can be a real challenge. And most of our circularity challenges require inputs from multiple different disciplines. So just thinking about the physical infrastructure of how we work together, but also the mental infrastructure, that we tend to be very focused on the thing that we do, but we have to be able to think about what others do in order to be successful in this space. And so I'll kind of kick that down the line to any of the other panelists that want to join in on that.
Yeah, I can add a little bit to that too. I mean, I agree with Angela, and I think working with growers, I live in South Florida and I work with growers all the time. The economics have to make sense to them. So the economics is a big part of it. What is my bottom line to have the circular system? What would I do with the waste? Does it make sense for me to put it back and use it in one way or another? So I just told you about this Tillage power, that makes this decomposable tableware. They're not making money yet. It's been a few years, but they will make money. They just have invested in this heavily because they think this is the right thing to do. So the social aspect is there, but the economics is very important. And I think what we lack also is involvement of social sciences. Talking about silos, we frequently don't involve social sciences to understand what are the incentives for our stakeholders to implement what they need to implement.
I don't know, Ziynet, any comment?
Yes.
Well,
I'm sorry. No, go ahead, please.
Okay, I just simply wanted to echo what Samira said, the importance of linking biophysical sciences with social science is paramount. We always give things for granted. We work in our own system, and we trying to here at the university, and you're all with me on this now, any project requires to have that integration. So from a research science perspective, we're doing a lot more of that. It is not easy. Sometimes even the communication between the two sciences is complex, but only by doing, we'll succeed. And again, also working closely with farmers. There is another commodity. I mean, number one is economics, but the second piece is time. So sometimes economics may not even be it is a critical and important driver, but if it complicates, we need to alleviate pain and not adding an additional burden. And one of the examples that I can never, basically emphasize enough is, for example, in high income country is the use of technology like the GPS on the tractor, the self-driving tractor, and be very precise, the adoption of tractors having GPS is basically close to 100%. It's in the 90s, because it just wasn't, it's saving money, but it's saving time as well. So circularity is the fact that we're talking about is very important, because it sparks idea and public-private partnerships, and I think we have to continue with this level of activities, making people more sensible. The consumers plays a role into this. And as I showed as an example, one component that is often, I guess, not paid enough attention in the ecosystem services is the fact that we're losing biodiversity. We continue to have, same looking landscape and so on. So changes that are even more abrupt will need to be considered in terms of rewarding farmers, because that, and there are initiatives at the national level where, 30% of the US land is going to go to conservation as either initiative or mandate, because again, the importance of biodiversity. But that's my
Thank you, Bruno.
quick thoughts.
Ziynet, you had a comment?
Yes, sure. I do have a comment about as we're trying to work together, I think the ontological aspects of this, so knowing the language, the heuristics poses a big issue. There are currently more than 100 definitions of circular economy, and then several other for circular bioeconomy. There's a lot of confusion around what circular economy is, what circular bioeconomy is, what bioeconomy is, and then how do we approach this? I mean, in Europe, for example, these concepts are commercial or like functionalized by the government and the policy support. But in the US, we are kind of fragmented, for example, or maybe, for example, there's a question about the developing countries. A lot of these approaches completely disregard the human aspect, the social capital, but its food systems is a very human centric system, food and agriculture system. And there are so many aspects related to human needs, designing waste and inequality out, and then designing systems that are serving several populations at the same time, not only aimed for high-tech, high-income countries. There are several research aspects going on, and then they call it circular humanosphere. I think those are some of the biggest challenges. As scientists, we know how to develop technologies, but especially from STEM, but if we don't come together with everyone developing these heuristics or ontologies, especially with the inclusion of digital ag and digitalization, will be challenging. So
thank you. There are some questions I'd like to pose. The first one is from Farah at AUB, American University in Beirut. Farah is asking specifically to Bruno, you could read that in the chat, but in specific, how is the technologies that you presented be applicable to small farm holders?
Yes.
I mean, here in the Bekaa Valley, a lot of technologies that you mentioned may not be accessible to them. So what's your comment?
It's a very good question. I think there is an important separation to do, which is, I present the technology that obviously are available here, the use of imagery, even though imageries are available even in, other countries, the sizes of the fields to, for example, make a decision using an imagery, they come in a much smaller spatial resolution that you may not necessarily need that level. I mean, it's much more captured, but what is critical is the use of a system approach. So any farmers that wants to make a decision would benefit by knowing what a potential outcome is going to be. So I personally work a lot. I spend time in India. I go often to Africa. I work with FAO. But the main approach that I work is using models for forecasting food, yields. And there are countries where there's no knowledge of how much food is produced. And so in that case, we use the exact technology that you saw, but to inform either government or the World Food Programme to be able to allocate, emergencies if there are shortages. From a tactical management decision, FAO, which has a great presence, in this, would benefit. They're not very much into using decision support system, driven by process-based model where they could run a what-if scenarios. But the literature is quite rich in understanding whether you use, pigeon pea in rotation with cassava and you use the stick. So there are lots of examples that I feel that they're not being transferred. And that's, again, one of the bottlenecks in communicating some of this advancement of sciences and technologies all the way to the, to the farmers.
Bruno, building on your response and inspired by Farah's question, what if at some point do you foresee sometime down the road, like big foundations that are having the interest of supporting these small farm holders, that they could own that infrastructure and provide the access to those farmers? Do you see that's a possibility?
Most definitely. And I think we have to be realistic that we should never necessarily envision a very small holder farmer, knowing the ones and where I've been, where there are very limited, connectivity, or that they will need to go and run their model, and run on the web, either on an app or something. But it's much more about training the enumerators or people working close to them to be able to tell them. The other message is an equivalent of a podcast. There are radio, they can inform. Today is the time to plant, so there are lots of technologies. Gates actually is one of the foundation that has invested in this type, and it's slowly moving all the way to the example that I don't know if you may know, but there is Hello Tractor in Nigeria, that it's like an Uber for tractor, you can call, and like most of Western Europe depends on third parties operator. No one owns a tractor, but there is one, group, one family, for example, that serves as the big machinery. So those level of connection need to be realized, and the governments play a big role. Nothing, it was mentioned before, solutions have to be customizable to the local situation, where there's someone that goes and help. We should really abandon the idea of bringing technologies with this colonialism type of approach. You need to use this as we will know better than them. It's actually the other way around, is trying to integrate their knowledge into a system that will work for them. And so I still, value the relationship with local authorities, which obviously, as you may know, it's not necessarily an easy task to do in those countries. But the technology is certainly available, applicable. It's just that we miss pieces of the tracks that we need to be able to have this train run fast.
Thanks you, Bruno. Basil, we've addressed the question, I think in my intro question to the panel. The next question is from Lina, specifically to Angela. Just a frame of reference, Angela, Lina is an animal scientist herself, and she's asking something specific to related to the consumer role in circularity in animal agriculture. And then she had a follow-up question with respect to animal production. Is it more advantageous for farmers to have more than one source of energy, such as biodigester and solar panel, as an example? Angela.
Yeah, so that's a really great question, and I can't do it justice in 2 or 3 minutes, but I'll maybe start it off. So the consumer role certainly has an influence on where things go, but I'm going to back it up just a little bit and not just talk about the consumer piece of it, and just talk about like providing protein to our populations. And I think the answer, the global answer is that there's not a global answer. That it's really regional because in certain parts of the world we're already overproducing and we're supplying way more than is necessary from a dietary perspective, but there's other parts of the world where we're not providing what's needed. And so I think in the long term we're probably going to see more variation in what we see in different parts of the world instead of more uniformity. So for example, I kind of threw in some alternatives into my talk to kind of think outside the box a little bit for how we're supplying animal products. So based on the circularity piece, can we ever get to a system where we're providing all the protein that's needed by just our traditional agricultural animals? I don't know that we even have to answer that question, because I think our systems are moving in a direction that we're seeing more diversity. We're seeing emerging ways of producing protein. And so I think a system we land at, whether we could do it all with circularity, is irrelevant. Can we create a diverse system that meets the protein needs of our planet? And I do think circularity feeds into that. Like, we have to fit this into all of the system. Animals play a huge role in the biological processes within nature, so excluding them is likely a mistake. But in terms of providing protein, I think we're going to continue to see our traditional ag animals, and hopefully we integrate them further into our circularity decisions instead of excluding them. But I also think the emerging new proteins are going to have a solid foothold in providing protein for the globe. So I don't know if you want to dive into that any deeper, but that's kind of my top answer.
Thank you.
Can I add something about what Lena is asking regarding if it's adapted to developing countries? I think if you look at systems like 30, 40, 50 years ago, maybe when my grandfather had a farm, it was a circular system because they depended on the farms and, you know, the animals, the farm, manure. It was a closed system more than we have here. Same things in India. I mean, they've been moving from a manure cattle system to a more fertilizer, inorganic fertilizer. And I think sometimes it has time to go back to the old knowledge that we had because it was more of a circular system at the time. Yeah.
Yeah, Samir, that's a great point. So, you know, in prepping for this presentation, some of the other things that we've been doing in this space, in one of the classes I teach, we think about the history of where we came from. And we came from these very diverse on-farm sites that had all these different things happen. That's the kind of farm that I grew up on. And we moved to these very monoculture systems where we do one thing, we do it very intensively, and we don't really think about things outside the box. And now we're moving to, can we do these things at that kind of scale, but better integrate them the way we did a long time ago? And I think that's kind of where we're pushing in the circularity space. It isn't, let's back up and not produce as much so that we can do it where we're integrated. It's, can we do at scale production where we're integrating things better so that we're not just being really good in one monoculture thing with disregard for all the other pieces that need to interface.
I agree with you, Samira, 100%. However, there's one caveat to the discussion, which is pollution. I think in terms of waste, reducing waste, in terms of recycling, the use of manure back to the farm, that's all fine. That's at the core of circularity. However, what some of these farms in rural communities have failed is in the pollution aspects.
I disagree. And I'll tell you why, because there is a lot of pollution from inorganic fertilizers. If you look at a manure as a slow release fertilizer, if it managed well, it can be very unpolluting. The problem is we use a lot of fertilizers that just go down the drain. So inorganic fertilizers are as polluting. It's just the amount you're producing. But look at it as a slow release fertilizer and no over applying, as Angela was saying. So yeah.
I mean, all what I'm saying is that the traditional farms are circular by nature. However, we need to look at pollution because pollution is important, and that's something that is so the concept that you brought up is very relevant, is very important. But we need to monitor the pollution aspects. It's not only the reuse. There is some excellent question that John has posed in terms of, are there perspectives to share on the role farm site and farm equipment transformation to electrification-based solution play a role in the circularity of bio or the ag bioeconomy?
I can take a quick tab at that. Is yes, I mean, you will probably know, John, that John Deere has basically created a fully electrical, system, tractor. They could become eventually at some stage, the norm. If you look at what is happening in the, the car market. The one thing that we did not discuss, and it's a little bit down the road, and again, we're all in agreement that regional solutions are the situation. Robotics is the next level of, innovation where this, self-driving, very, in the case, with Angela, we share we're part of this AI Institute, and I work with, colleagues in the robotics as well in the economics. Robotics that can pull weeds that are now resistant to herbicide, and they have basically no emissions. And so the future is going in that direction. And again, if you see in the papers that I was suggesting in the end about the egg system and the PNAS, we cover a big component of electrification, even of fertilizers, creating energy where, fertilizer could be produced from energy on the farm on a small scale. There is a prototype of creating liquid fertilizer from solar panel. And so it does about 5 kgs. But anyway, the direction is certainly going, and you centered the point for sure.
Thank you, Bruno. I'd like to pose a question specifically to Samira because of her background, and this is a reality check. If you look at fertilizers, we're talking about circularity, but if you look at the global picture with the food security, with the food insecurity, especially in Africa, a lot of the insecurity is related to the lack of fertilizer. In fact, because of a farmer's small share of whole farmers, they don't have access to fertilizer, so their productivity is low, and that's a vicious circle. And in particular, I'd like to focus on phosphorus, because phosphorus is a non-renewable resource. There are very few sites that has a production scale that can be used for fertilizer, and yet it is not a renewable resource. We tend to ignore that fact. So what's your perspective in terms of fertilizer use? Forget about the pollution aspect. I'm talking about those who need to use fertilizer and they don't have access to it, and as such that they're not in that production zone. What are your forecasts?
So two things. I mean, this is a big question, and I think there's a lot of research still need to be done. We used to have, he just retired, Pedro Sanchez in our department that talked quite a bit about phosphorus chemistry in tropical soils. And it's really misunderstood that there's not a lot of phosphorus there, because there is quite a bit of residual phosphorus that has been added. We need to tap into that phosphorus. And the focus, and I just mentioned, the focus on the research is to be, how can we mine that phosphorus? And I think it has to be with plant breeding. So plant breeding, which as soil scientists, we don't really focus on, but it's important to have these crops or varieties that can mine phosphorus from residual long-term, phosphorus that is unavailable. So that phosphorus, yes, it's residual, it is there. The research has to focus on plant breeding. Can we solubilize that phosphorus coming out of that? The second part of it, I say, which is the management of organic matter. So this is where, if you don't have inorganic fertilizers or access to it, do you have manure that can be treated? So I agree with you what you said last, just that Rabia, food safety is a big issue with manure. I was just talking about leaching of nutrients, but not as much contamination from manure itself. But managing organic matter and mineralization of organic matter can release nitrogen and phosphorus. Not depending on monocropping, but basically put more of, simple solutions of adding more nitrogen can enhance also the ability of those plants to sequester and get phosphorus out of the soil. I think it's a really pronged approach to distribute fertilizer, management of organic matter, and try to plant breeding to mine more of that phosphorus from the soil.
Thank you. Thank you so much. Let me just, before we close, there was one question from Farah to Samira specifically. What's the scale that you would recommend for these practices that you mentioned, small scale or large scale, and what would be the best location having these wetlands? She's specifically talking
about. So Farah, I'll email me and I'll send you more information. Though these constructed wetlands in South Florida are huge. We're talking in acres, about 45,000 acres. They have like 6 of them. They're meant to be large to really clean up the water. So mostly they're used for water quality. But I have seen small scale wetlands constructed in India, for example, to be able to clean up wastewater. It was not very successful with Ecrisat, but we have some information on that. So it could be a very small scale, treating wastewater from a village versus what we have in South Florida, billions of dollars invested in it. But I can send you more information.
Thank you so much. Thank you for all the panelists. It was wonderful. Thank you for all the audience. Great discussion, great presentations, lots to do to get to the circular food and agriculture system, but I think it's a journey that must be done, as all of the speakers highlighted. Thank you so much.
Thank you, everyone.
Thank you, Rabia, for organizing this.
Yes, and ASAB.
Yes.
And ASAB.
ASAB.
Joanne, thank you, Joanne.
Thank you,
Bye,
Joanne.
everybody.
Thank you,
Nice
Darren.
job. Sure.
Thanks.
Bye, everyone.
Stop recording.
Maybe we can stop recording here. Oh.